Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. If you have any questions, you can post them on Twitter or YouTube and I'll be there to answer. Alright, so let's start with this and open the project. So the last thing we did, we were playing around with, I believe, the bounce instruction. So if we run the debugger, we can see where we left off. Not now. And so if we run this, you can start seeing what's gonna happen here, which if I were okay. Now where we are, we see that we print out the bound instruction correctly. Now to do that, we happen to have a problem, I believe, I remember, on the fetcher. No, it was on the fetch memory operand thing. Well, it was, oh, I remember now. Oh my god. No. It was here because yeah, it was ESI, which is, that's the wrong thing. So let's go back and do the correct stuff there. So let's go to fetch memory operand. Fetch. There you go. So over here, this is the place where we left off. In fact, we have, there you go, here's the you are here. Okay, I have to have a better, like the you are here flag, so I can just say you are here. Yeah, probably that's better. So if I say that, in fact, well, I can just erase that. You are here. For example, this has another you are here, which is not probably what we want. So fetch memory operand. So yeah, anyway, so this place over here, where we say fetch register operand and we fetch for an index, that's okay because we are gonna have to do that whenever we have an addressing mode that has an index, which in this case is I think always. Well, not always. Sometimes they chose displacement and stuff, but yeah, so it's not always, but most of the time, or many of the addressing modes have an index mode. So that's okay. Now, we control that. The problem is that here we have a fetch rn field, which by default it's and in fact I don't know if it's no, this is not the problem. The problem is where is it? Well, this and and this. I mean, because this is biased to always go for the SIB byte, which is not the case because we should only do that if SIB present, you know. So it's a two-way go here, so we can just push all into here. Now I believe this is okay here. It has a two pass in there. For example, first pass we go and fetch for the RM field on the base. That's because the base it's on the RM. Well, the base is in. The base is in. Let me go here. Yeah, the base is on the top part, and the index scale is on the other part. So it's just that. So if that's the case, so you can just say that this is gonna be false. All the time, you know, it should be. Whenever we go for the index, it doesn't matter if we are on the mod, you know, because we have this thing as well. So we always are going for the RM or the index in this case. So this should be true. I mean, here we're going for the RM field. Now, how do we did that? Let me. If we go for the fetch RM field, we go for the base. If not, we go for the index. Okay. So I think that's busted because it's the other way around, isn't it? This has to be the index. This has to be the base. you know. So if we do it that way, let me make the transformation. Just because, I mean, following the idea that the index always goes on the RM field, you know, so that's the way it should go. So here we have the RM and the other is the reg, so that's correct. Index to base, that's correct. So if we do it that way, we should pretty much fetch register for example here we pass it just straightforward over there, so that's okay. Here we have it and we say that normally we're gonna go for, normally in this case it's true, you know, we're gonna say that's true because that's the most common case, and this is gonna be false, and this is also true in the most common case probably, so we can just say that, you know. And over here we have all this stuff, you know. Let me see where we have a fetcher and stuff like that. So whenever we have an SIB present, of course we have to say that fetch more and by is gonna be false, and that the fetch RM field for this case is the base. That means that it has to be false as well. So, and SIB by present, something that we do here just for incrementing the size of the checker, so that's okay. Base size effective, this is the base size, which is the modifier that we use as a checker, and then this all okay, and here we push a string, which is okay, and then we will go for the index. Now the index, normally in most of the cases we're gonna fetch something there, but it's just if we have an index size invalid, that will be the it wouldn't get anything, you know, so that's okay. So here we have to say that it's true, you know, because now we're going for the index, so it has to be true. RFC modes as well. I can erase that, and fetch model and by. This is a place where it's okay because we start with true. If we modify here, that's the way we want to keep it, so we don't want to modify that as well, so it's just like that. And this is all the same. This is a consequence of fetching the index. If we got a scale based upon the SIB by present, we do this stuff. If not, we just have an adder, which is something that we push. Now, and then we have a displacement. Over here, well, the idea is because we have, where is the plus? Here's the plus, and then this is the thing. But it could be the case that we need to, if we have a displacement, let's say, just if we have a displacement, this is the thing that we have to do. So it could be here. And we have this, so we don't need this anymore. And all this stuff should be the same, isn't it? Displacement, bad size. Well, displacement, it doesn't matter. It's independent in that case. So we just like play around with it. And all this stuff happens to be consequential for the displacement size. Then we have the pushing thing here, which is okay. And then the operand offset, which has the SIB by prism, that's okay. And that's it. So let me just see, we don't have a base in here, you know. Well, this has a base, which is exclusive for SIB. Here we don't have any base, you know. So that's it's okay. It's just the index that it has to be both of them, so that's alright. So let's compile that. And here we're pushing the string. And that's all she say. So if we see this, let's try to run this again so we can see. So this is gonna be the same. We get a valid entry. Let's see. Yeah, it has a bound. So we go for the fetching of the memory operand, and we're gonna start saying that we have a modern byte true, you know, and there you go. If SIB by prism, it's just gonna be false in this case, you know. And then we we don't have a displacement, we don't have that, we assert that, we push a string there. If SIB by prism, we just go and say, well, we have a result, yes we do, and we go fetch for the scale. We return the result, SIB by prism equal true, and then fetch modern byte is going to be false, fetch current field is going to be false as well, because we're going to go for the base. And if we see what we got on the buffer, we got EBX, which, if we remember, I don't remember which was the instruction, so let me see. I got it here. Yeah, it's EBX on the base. Now, well, I can close that. Yeah, we have EBX. We get a plus, push a string. Then we're gonna fetch the iron field. Yeah, that's a common case. Then we have ECX. We have the scale. We have times. And we push the scale as well. We don't have a displacement. We close it, and we have that. Okay. We fetch the register. We don't have that. Well, probably we do. I don't know. Yeah, it's EAX, isn't it? Yeah, it's EAX. That's correct. We don't have any immediate, so this should be just null. So we print instruction. It's an EAX. It's a bounds between the memory range that is in the memory offset of EBX plus ECX times 2, and the data index that we want to compare against those bands is stored in the EAX register. So that's alright. So let's go to the next instruction and see what happens. I don't remember which instruction it is. Let me see. It's NAT. Okay, so it's a NAT instruction. It's correct. So we go in fetching this AND instruction. I believe if this is the one that has an immediate form, you know, and probably also has a quirky way to express it. I know I should write all the things, all the mnemonics that I'm writing, so I can remember how should it be, because if not, this is gonna be bananas. So that's the next thing I'm gonna do. So this is blah blah blah, and then there you go. We have a memory operam. So we just go the same way here. Here we have a displacement of 8, and we had push string. Here, well, we could say that we don't have any scale at all. We're gonna fetch a register operam for the RM field, which in this case tells us that we have EAX. Okay, EAX, that's okay, I believe. I don't remember which is yeah, I think it was EAX plus displacement A, something like that. Fetch register operam. Now we didn't print. Oh, okay, that's okay. Now plus okay, okay. Okay, push string to buffer. There you go. We don't have a register. Oh, we do. Okay, that's busted, and that's probably busted because of the RM field. Yeah, because it shouldn't be AL. So here's the problem. Now fetch RM field, it's false. And what's the operand size? It's 4. So where do we get AL? Is it AL? It was, I don't remember. Yeah, it has to be AL, isn't it? Because let me put her. Because we have a a memory that is 8-bit, you know. Now the problem, no, but yeah, I remember it was the add thing. It was a quirky, but it was an 8-bit, which it didn't need to. No. This is the bound, which we already got it. So well, I think I was closer than that, you know, but well. Uh-huh. We have Elvi carrying, and this is the end. So we have, it was this one which we define it. We have an immediate register, and we have, so yeah, we don't have a register. We have a memory register. That's the thing. So we have that busted. So let me go back into there. There you go. This is the mem buffer is EAX plus FFFFF0. Now the memory open, you know, it's NAT, and that's okay. Yeah, the memory open, that means not the address open, so that's okay. Now let me see what we're passing here. Effective operand size, it's 4, that's okay. Mother and byte, it's true, and the RM field, it's false, that's okay. So let's enter. Now you gotta register operand size, it's a byte. And the problem is that well, I don't know how we were doing this before, but I mean, of course it's gonna enter because we probably changed something, but we pass all things the same. So if we enter here, this is okay because we mod, well, it says that it has a register operand size of blah, you know, which is not the case. Well, what can I say? I mean, if we enter here, this is just gonna say, well, we have an effective operand size. If we do, then we just go into it, and it's just gonna go and do it, you know. We then get the index, we have a fetch mother and byte, and just say, hey, give me something. I give you something, and which is of course 1 byte, so it has to be L. So this is correct. The problem is that on this part we should have something better than just this. It can be that since we have an immediate, you know, if you remember, this instruction has the thing that actually this instruction is quite nice because it exemplifies one of the problems that we have right now, which is that we pretty much go straight forward looking for, you know, as if the immediate size, or if we always have a register operand, which is not the case. So in this case, this instruction has a memory operand and an immediate operand. So we have to do something here special to say, hey, we don't have any register operand size, so please don't print me out anything there because I don't have anything. And in fact, well, we're gonna move up fetch count more, and if we do that, well, I'm gonna put string AL, If we do that, the fetch count now will be turned there. So here we don't check for the fetch count, which is kind of interesting. But this is OB, yeah, that's correct. And that's all she say. Now we print instruction, and instruction is gonna be all bananas, which doesn't has any AL. So this is okay. Now let me go see the instruction. We have an 80 40 F0 OB. So is the standard opcode thing. We have an 80 there. Then we have a 40 there. Then this is the modern byte, which is 01000000. If we go and look for the modern byte, in that case, yeah, we have EX plus displacement, which the displacement is sign extended. So the displacement, it's something that we sign extended, that's correct. And then on the other case, if we had the rec, but now we don't have the rec, which is the kind of, yeah, because you see this is A also, yeah. And then we have a displacement. That displacement by itself, if we go and look at it, or say the end, it has to be immediate to memory. We have on the, it's 80, that means that is not I don't remember. It was W, I mean W with W bit is equal to 0. That means that the value of the the value of S is not sign extended, isn't it? So S is not sign extended. And the value of the registers or the effective operand size, which is this. But this is for the rec, isn't it? And we are not using the rec. This only affects the rec. I'm sorry. So when W is equal to 0, we have an 8-bit thing. If not, we have a full length thing, but just for the rec, you know? Yeah. So that's good to remember. W bit is just for the rec. If W equals 0, rec, we have an 8-bit GPR. Otherwise, we have a full GPR depending on the operand size attribute. Okay, that's good. So that's good to remember. AHCH below canonical REX. Okay, that's also good. That's important. AH, CH, DH, PH. Can I be encoding? When REX prefix is used, suction expression defaults to low byte. So that's good because, well, we don't have a sign there because it's 0, so there's not gonna be sign extended, which could be, and yeah, I mean, right now since we don't sign extended, it's gonna be the case here, so that's alright. Now let's go and solve for AL in that case, which, I mean, the pretty much simpler thing to do there is that normally we'll have a register open size, and we can encode that in the entry, because that's something that it's possible for this particular instruction, which has this particular field. So let me go to the load, initialize. Where is the F? Here you go. We have a rect to model RAM, immediate size is byte, register to operand size, it's a byte. So this is the problem. It's okay if we get the memory operand size. I mean, this is not like the effective operand size idea, So yeah, we have to be pretty much clear of how we are using this stuff. So because we can say that it's 0 size or invalid, and therefore we will get that the effective operand size is the one used, but that's not the case, because in this case we don't want to get something like that. So what we could try to do is just to change this so that where is it? On the tables. We have an invalid there, but I want to have something where much bigger. Can be now over here. The reason that we have a register operand size or whatever is because sometimes is the effective operand size that has to be used, or sometimes it's the other one, so right now I don't remember which was. I mean, we were using it, but we have to start to define that more properly. So I think that if the register operand size is the one that tells me that it's 0 or invalid. We can say that's invalid. We are not gonna use it, so we have to say something like this. And if we have that case, so this 0 is more like, it's not really 0, but preferred, or I want something more explicit. Data size effective. So if we say that it's data size effective, and that's, I think, better expressed. Now if the value is 0, well, I mean, we can have a better value for that, but yeah, I mean, that's okay, because we have an invalid also as well. I prefer it that way, because the invalid thing is like super clear that we have a value. The effective is like, you know, we can use this, or the effective open says it's more like open, and the others are just deterministic, you know. So yeah, I mean, that's good. So what about then? Okay. So let me. Shall we make something more clever here? Okay, probably yeah. Yeah. Okay, fetch register operam. Now this fetch count should be also here as well. The reason that we don't use it, no, where is it? Fetch immediate operand. Just for the case f. Okay, and now we can say over here we have a fetch register operam. So now we have to fix the whole data set so it it works with the new idea that we have. So I have to go to the data set and go one by one. So it's gonna be a little bit I don't even remember, so let me see. For example, fetch register that says invalid, fetch immediate, if effective immediate size. Something more like that. And if that's the case, so this is a perfect occasion to change these effective data sizes to something that uses the data size invalid, the data size type, which is what we were trying to transition there. So we want to do that, we can just say, well, over here I'm gonna use the same thing. Okay, so if we do that way, just keep the symmetry there. Now here we have an effective address size and stuff. Should we don't use it? Oh no, yeah. No? Super weird. Effective operand size. Oh my god. The effective operand size, we do use it. So we don't use it because we haven't do the 16-bit addressing mode. So this is more like here, something changing there, but well, I'm gonna keep it there. It doesn't matter. Yeah. I mean, it's a little bit different the way it works, but it's okay. Set B by present, that's okay. Fetch register open, that's okay. This is the one we changed, so now we just validate information, and we have a CO byte, entry register index A. Yeah. For example, here is I can do the same thing. Let me go one step by itself. Let me do this, and this, and ready to that, and alright. So then I would like to move this like this, and do that. And then we can say, you know, let's go here and change each one so it uses the same data size thing. For example, and this is important because now let me go to tables. I mean, it was the nice thing because we didn't need to write it now, but probably we want to keep it well, I mean, I don't know how the file, well, the data, this thing that we're gonna write we're gonna write a file system to write all the entries and stuff, but since it's nice not to have to write it, I mean, we can do just this, but we have to be careful. So yeah, I think I'm gonna go to the other way. So where is it? Data size. So I'm gonna go the other way around. Yeah, I like it that more. So we can keep it the way we have it. It's just like, hey, we're just gonna check it that way. And yeah. So that everything else is gonna be just kept the same way. And yeah. So yeah, I mean, I think that's it's the same. So let's compile and try to run it each time. So debugging is just gonna be our savior here. So let's go and do that. It's just straightforward. So let's go with the first instruction. We have first, la 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 la. You got an entry, which is a bounds. It has an invalid immediate size. That's okay. Did we change the immediate thing? Let me go and fetch immediate open. Yeah, we have, yeah, okay. Okay, so begin operand instruction, fetch memory operand. Just gonna do its magic. We can see the data information going out, ECX times 2, displacement per string, and there you go, assassin, operand offset, and stuff like that. Okay, now fetch register operand. Register, here we have a word. It's okay. We have an effective operand size, which is a door as well. Fetch register operand. There you go. EAX, and return the result. Fetch immediate. We don't have an immediate, so it's null. Hit print instruction. Oh my god. And it's the same thing as before, EAX, EBX plus ECX times 2. That's correct, that's correct. So now let's go and see the CBY. CBY is pointing towards 80, and that's okay, it's normal. So let's see what happens now with this instruction. We have a nav, we have a modern preset, and then fill. Well, we don't use that anymore, we can just get rid of that. Back mother RAM. That's okay. We have an, oh, did we change the, yeah, we have invalid. Okay, memory operand size is invalid as well, so we probably want to do something about that. But yeah, fetch memory operand, then we got the mother byte, and there you go. Dun, 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 dun. We're not gonna have an SIB byte. We're gonna do that, and we're gonna get EAX. We have a displacement plus blah 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 blah. There you go. There you go. Now for each register operand size is null, so we just return the result. And fetch immediate effective immediate size is gonna be it's something, so we can just bring it down OB, and that's the way it should go. So now we have an OB EAX plus FFF0. There you go, that's correct. And so now let's go to the next one. C byte is the 5. That's correct. I don't know which instruction it is, but we can see it's an AAAD, adjust after division. It's correct. Begin a parent instruction. This is, I don't remember. It doesn't have a memory operand, or at least it's it looks like. Let me see what it has. It doesn't have, well, it doesn't have any mother and present. Okay, so yeah, so that's the problem. It's not gonna have any mother and present. So in this place as well, the register operand size is just invalid as well. The immediate operand, we do have an immediate, so we can just bring it out. So yeah, I mean, that's the whole thing of the instruction. So C byte now it's on the 8. That's correct. We have the 8 there, so this is another floating point. Well, this is a floating point instruction. It's a FAF, yeah. So this is a mother and present 0x001. Yeah, alright, so let's see what happens here. So we didn't print anything, which is kind of funny. So let's see what happened there. The operand size is 4. The buffer size is blah and blah. Oh, it's because we're using that thing. So let's go back and run it that way. There you go. The entry is a FAF. There you go. So let's enter see what happens. So this is the problem. The entry has a register operand size that's invalid. So probably that's the problem, because this instruction should have a register operand size. So let's change that. Let's go to FAT. Now we don't have floating point, but we can say floating point double extended precision. Which it's the we can say that, I guess, tables. Data size, center point. Well, yeah, I can say, I don't know if we're gonna use them, but floating point. We could, you know, probably we want to do something smarter there. Probably. Floating, well, this is gonna be single precision. Floating point, single precision. It's gonna be 32, which is data size, the word, FSP, FWP, FDP, data size, core, and this is 80. And we're gonna say that, well, FDP, say. Right now we don't care about that. Register opens FDP because that's the real size, you know. The registers are that size. So yeah. So yeah, FDP for that case. Probably FUCOM is equally the same thing, you know. We have to have a register thing, which is FDP. I know, you know, it doesn't have a memory open size, register open size, and then yeah, those two have to be like that. Here we have a memory open size, so we probably have to think more about that. We are not using it right now, so it's okay. Let me just go that way. There we go. So I can just go straight on there. The other thing looks pretty much the same. That's good. EAX, EBX, CCX2, EAX, FFFF0 of B, AADOA. So if we enter here, we have a register open size, which is FDP. That's correct. We go for the result, which is just for making sure that we have something legit, you know, which is nice. I mean, it was something that we needed to do once in a moment, you know. So we got the result, and let's go straight on to push it. This is S to 0. Plus equal operand offset. There we go. This is, oh, did we get a problem there? didn't get anything. We didn't get anything there. So one more time. There you go. From here we got him. What? Alright. There you go. And here's the problem. There we go. And here's the problem. What's the problem? We have a mother in prison. It's different to the results invalid, and the fetch count is the problem, isn't it? Okay. So the fetch count gets moved 2 times. Oh, hold a second. Where did we move the fetch count? We got it on the immediate, and where else did the fetch count was busted? Here, isn't it? Here we have also the thing. Where is it? Let me find it out. Of fetch count. Here we check it. Here we move it. Oh, here's the here's the problem, isn't it? Since we're moving it on the other side, we have the same problem, which is not something that we would like to do. So we could, if that's the problem, we just can say that on this side, fetch memory open, we're gonna say this. Now the effective operand size has to be chosen based upon the data type. So I would like to say where is the fetch count thing? It's here. So, well, I'm gonna leave it there. That's okay. I'm gonna move this here, and that's it. So there you go. Just like we're getting sense of all this stuff. So don't worry, we're gonna clean all this stuff later. So open the buffer. There you go. This is alright. This is alright. Yeah. So we can even well, no. Obviously, I was just gonna say, where is it? I cannot open it. I don't see why do we have this open offset. Do we have oh, okay, because that's the way we do it. Okay, yeah, these the things have to be transformed a little bit. So yeah, so I think that's it. Can just go and go straight down to, whoa, what happened there? We are on O3 now. What is O3? We're on the last instruction now. That's a little bit weird. Okay, so we have an F-low 04. We are resume line XMM0. Here we have a problem with the XMM0. This should be XMM1. So we have to check that. The other things look pretty good, I believe. This shield, I think this is okay. This register, this thing looks totally busted. So we can go to the P line and check. So let me go to the P line, which I don't know which is, I don't know which one it was. So this is the last one. It should be rather OF or 66, isn't it? Let me run it back again. So it is 66. So let me put it here. Alright, there we go. We are on 66. That means that we have printed out all this stuff, you know, ST0, ST1, blah 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 blah. We're gonna resume stuff like that, you know, simple stuff. So we move past over the mandatory prefix that the instruction had, and we say that we got an entry which is P line. That's okay. Now the P line thing has an XMM on the memory and on the register. That means that has 2 registers and it has an immediate byte of size byte. Okay, that's good. It's using the whole flash of the flavors. So we can just go into it, you know, what happens. It should be a register. So let's go and do it, you know, something should happen here. We are gonna enter and we're gonna get the fetch mode mother and byte and there you go. So this is gonna be something, let's see. This is the problem, is ECX, so the fetch register is the problem. So let's see, why are we missing something? Well, the effective operand size is busted, isn't it? It shouldn't be that size. So where do we pass the effective operand size? It's 4. That means that we pass it from there. That means that we use it up here and we pass it from here. And the okay, no, my bad. Yeah, we my bad. My bad. I said that we didn't change that, and I changed it. So my bad. My bad. Okay. Now one more time, please, if you would like to think about it. Oh my god. What's going on? Why do we have two ads there? Okay. Okay, now we have the correct things for XMM0, XMM1, and this looks correct as well. BM resume, PLI, blah blah blah. The shield, yeah, the displacement is correct. The immediate, if it was an immediate, is not correct, or at least I think it was something different. And the add instruction had something different there. Yeah, so let's go now to the shield. See what happens. See what happens. So the shield is one before the last one, so shield has to be it has to be this. Yeah. All right. So okay, so let's see what we got here. We have OF, and that pretty much tells us that we should be, well, let's see the entry. We are on the we are in the BIM resume. The BIM resume also has that. Oh yeah, okay, so there you go. Now let's do that and see what the entry. Okay, we have a shield. The shield has a mother RAM, doesn't have an it has an immediate size of a byte. Okay, and yeah, we have a problem with the register operand size probably. Now the shield is a memory operand size, so it's not going to be a problem for that. The problem is the immediate. So let's see. Well, let's go first for the memory. You know what happens. It should be some memory there. You know, it's we don't have a displacement. Well, we have a. Oh yeah, no, my bad. We have a 32-bit displacement and index size invalid. So we don't have an SIB, we don't have an index size, so that means that we're gonna go there. We're gonna have a displacement, so we just put an add there. And we're gonna push string to buffer of whatever we have there, you know, 32 bits, so it's just 0 0 0 0 0 0 0. So we see this, we have a 0 0 0 thing, we close the brackets, we move around, and operand offset is 2. 2? How huge was the displacement? I can't see this. Oh my god. No, but the displacement, it has to be 32, you know, because that's the thing that we define here, which is 4. So we are not moving correctly the upper and offset, so probably that's the problem, and probably it's because of this ternary. So I wanna go and modify that just to see. Fetch memory open. Okay, one more time. We're gonna get to there. There you go. We are on the shield instruction. There you go. So we have a displacement that it's 4, and we're gonna do the magic here 4 times, and we have an upper and offset which is 0. We have a displacement which is 4, and which should be 5. Okay, now that's correct. Of fetch cam, there you go. Now fetch register open, we don't have it, so this is invalid. There you go. We have an immediate open. That means that we have to fetch it, and there you go. And then there you go. If we print instruction, there you go. Now that makes more sense. That was the problem of it, a typo. So CBAT now it's pointing towards 0x03, you know, it's good because that's the last instruction, which is the add instruction. And let's see what happens, you know. Print it out. This is an add, it's valid. We have register operand size. It should have a register operand size, isn't it? It's moving from memory to a register, I believe. So from memory we have a mem buffer which is 000, and from register we should get something there. So it doesn't have, oh my, okay. Yeah, it has a modern preset, but this is the place where it's gonna do bananas, and it doesn't have an immediate, so the print instruction is just gonna be busted. So that's because of the encoding. So let's go to the add instruction and change it as well. So it's this one, and register operand size, their size, store. Memory doesn't have it. We don't care about that. 2, count, string length, add string, good. So now let's see what happens. there you go. We have EAX plus 0, 0, 0, 0, 0. Now the thing I don't remember, and I want to make sure because of that, is that the first instruction was, if I remember, let me try to find it. It's not gonna be hard to look at it. So this is a 1 byte, 3 byte. It's the first instruction that we disassemble, so it has to be this one. It's an add instruction 03050000H. So it's a word or double ball depending on the operand size attribute. The second operand type if it indicates a mother and byte. So yeah, this is the this is not correct. This is more like effective, yeah. Which is our special case scenario. So yeah, that was the only thing that I was like trying to think about. Like, yeah, no. Oh my god. What? Okay, whatever. So let's compile. Let's compile and see. Boom, boom, boom. So the result is the same, but now we are correctly have an idea that you have to check the effective in this case. So there you go. The other thing looks pretty much good. ST1, FLD, XMM, blah blah blah, tree, whatever. A3OP, blah 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 blah. And that's all she said. Okay, that's look pretty nice. That looks pretty nice. And I will print the bound instruction with all the other instructions as well, with a special SIB thing, which has a way to do it. Now we have to do something with the plus thing here, because now since we're printing it out always whenever we have a displacement, we don't want that. We want it whenever we have a consequence afterwards. So let's do that. Let's do that as well. And let me, before I erase this, because I want to write it so we can have it. I don't know. There you go. This is our instruction string. Alright, so now Let's go to fetch memory operand. And over here we just need to now let me see. For example, here on the base, if we have a base, for example, let me see. If we have a base, we should have an index, isn't it? We could not have a base and have an index, but if we have a base, we will have an index and a scale. So that can be solvable. Now the displacement, we could have a displacement alone, which is this case, or we can have an index, a whole thing with displacement, you know, can be the whole thing, base, index, scale, displacement, or it can be index plus displacement, scale, index plus displacement. So this has to be thought as you can do that. And there you go. So yeah, so there you go. So now we have the same thing we had before, and we're starting to see that little change that we wanted to see. You know, like we're starting to make the transition for the sizes and make a definition for it inside the entries as well. So I think I like that. So yeah, we're gonna continue with that. So well, this is the reals, so I'm gonna copy just because yeah, one more time. This is the reals, you know, the current reals. And you have ADAX 000, whatever. And that's pretty much it. So if we do that, we can just go pretty straightforward into there. So one thing, let me see if we have time to do this. I would like to where is this? These all things, I want to change them. We don't need that anymore. So I want to say I want to say that I want to compile with that, and let's use a compiler to solve all this. So this is going to be 32-bit. There we go. This is going to be data size invalid, data size invalid, data size 32-bit, effective byte size invalid, 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 data size invalid, data size 8-bit, data size 32-bit, data size 32-bit, data size invalid, data size 32-bit, data size 8-bit, and here data size 32-bit, data size 64-bit, effective operand size override prefix prism. So let me just change this data size 64-bit. There we go. Compile. Data size 32-bit. And this is data size 16-bit. Alright. So let's compile. And if everything is right, we should pretty much do the same thing. So we can make the match against this. We have a bound EAX EVX plus ECX times 2. You have an add EAX plus FFFF0, comma 0B, and OA, F add ST0, ST1, FOCOM ST1, ST0, FLD 00000004, 00000004, VM resume, P-line XMM0, XMM1, OA shield displacement of 00000000, O3, and at EAX 00000000. Okay, perfect. So it's the same. So that means that if we go, I don't know if it was here, yeah, can read that, and that's all she said. There you go. So there you go, we get our stream back again, and we make some cleanup there, some more definitions, and that goes well. So yeah, so I think I'm gonna stop here, but if you have any questions you can post them on Twitter or YouTube and I'll be there to answer. Please make your questions relative to the thing we did today so I can answer them. And yeah, yep, I would say thank you very much for coming. I think that on the next stream we will continue making this. We have to play around a little bit more, you know, more SIBs, more data sizes, you know, more of that stuff, you know, more weird stuff going on, you know. We have to try all, you know. That's the thing here. So yeah, so thank you very much for coming, and I will see you all on the next stream. Take care.